Going into Chapter 4 now, Topic 1, Systems of Linear Equations in Two Variables. Here are the objectives. Now, this is in background thinking that we normally have one equation, but how about if we have two equations? How are they going to relate to each other? And a general background scenario might be that you have your graph and you have one equation that's represented by the red line, another equation represented by the black line, and an interesting thing happens at this point. They intersect so that the ordered pair of the red line and the ordered pair of that black line, that unique point, is in a sense a solution for both equations. Now another scenario would be that the red line's one equation, the black line's another equation, and as we see, the lines are parallel. There never would be an intersection. And as we go to our last scenario, we see a red line, but suppose if we graph the other line and it was right on top of it, you might say, well, the solution for a red line is also a solution for the black line because, in a sense, they're the same line. So there would be an infinite number of solutions. So these are the scenarios that operate visually in the background of this particular lesson. So going back now to an earlier lesson, here is the standard form of a linear equation in two variables, x and y, and they are a straight line. So these are what are called linear equations or linear system. And we're looking for a situation in which there may be a point where these two equations intersect. And if they have at least one intersection, it's considered a consistent system. And if they are parallel lines and will never intersect, they are an inconsistent system. Again, some key background vocabulary. In example 1, the first thing they want us to find is if we had this system of equations, is this ordered pair a solution for both equations? So the protocol to solve would be to substitute the x with a 1, the y with a 2, and as we see it laid out here, this becomes a 2, this is a negative 6. 2 minus 6 is a negative 4. So in this first equation, that is true. Now we take the 1.2 or 1 comma 2 and put it in the second equation through substitution. There's your x replaced with a 1, your y with a 2. So 2 plus 2 is 4, and this is true. So again, this is sort of the check to see if an ordered pair is a point of intersection. Now in example 2, we're going to do a similar thing in which we're wondering, is this ordered pair a solution for this same systems of equations? Well, when you replace the x with a 7 here, the y with a 6, we get 14 minus 18 is a negative 4. And does it equal negative 4? Yes, that's true. So this is a point in this equation. But when you take that same set of coordinates and put it into the second equation, replacing the x with a 7, the y with a 6, we get 20 equals 4. That's not true. That's false. So this would not be a set. Now, one of the two algebraic methods we're going to use to solve these systems of equations, and we'll be doing that in future lessons as well, is the system of substitution. Now you can pause and read this. It goes through the protocol, but I will be showing you what that is like. So here we're asked to solve this system of equations through the process of substitution. So what I'll do is do it on the whiteboard so you can see it in action. So this is example 3, and we'll go to the whiteboard. Now, as you inspect these equations, you want to see if you can solve for one of the letters. And this one is the obvious example that if we write it y, which is this y here, and just transpose this 2x to the other side as a negative 2x plus 1, we have solved one of the equations for a given letter. Now, we have a value for y. So there's our value for y. We're going to take this value for y and replace it in the other equation right there. And now write this equation with only the one variable, letter x. So we get 3x plus 2. Now it was 2y, but we know that y is, in parentheses, a negative 2x plus 1. We have substituted. That's where the process gets its name from, and that equals 4. So now we have 3x as we clear parentheses minus 4x plus 2 equals 4. We only have one kind of variable. So we do this subtraction here, and we get a negative 1x. Usually we don't write the 1, but I'm doing it for calculation purposes. Transpose this positive 2 to this side where it becomes a negative 2, where this side ends up being a 2. Now we want to solve for a positive 1, so 1x. So we're going to divide both sides by a negative 1. So we get then x equals a negative 2. So we have one member of our ordered pair, and we just need to find the other. Well, we know if x is a negative 2 times a negative 2 here is a positive 4 plus 1. Our y value then is a 5. And we have solved this set of linear equations by the process of substitution. All right, let's go to our original board, and they're showing us, and keep in mind, let's write that ordered pair. So they've done what we've done, and they get that x is a negative 2, and we substituted that negative 2 into the other equation, and we get then our y value is 5. So there is the results of our first example through substitution. And doing the check that we illustrated earlier, putting these values into each equation, we see we end up with a true statement. Now, that's one method of finding the ordered pair that would meet both equations as a true solution, that is a point of intersection. There's another method that we call the addition method, and that's summarized here, and I'll show you what it's like. And we'll do this one on the whiteboard too. So again, we start off by being sure both are in standard form. That is ax plus by equals c. And we see that is the case. And we've written out the equations, and there is a protocol for following. Number one, they're in standard form. Now here's where you take a moment to inspect and brainstorm a little bit. You want one of the letters, if you were to add these up, to cancel out through the process of addition. This is sometimes referred to as the process of elimination, where you're eliminating one of your variables. So you end up with an equation with only one letter, as we did with substitution. Now, studying this and looking at it carefully, I see that, for instance, if this 2x were a negative 4x, these terms, when I added them up, would cancel out. So that's what I'm going to do. Now, what I do is I put a little arrow here. This equation I'm not going to change at all. So this just becomes 4x plus 5y equals 3. But this equation, and I'm going to erase this, and I'm going to multiply, I'm going to put a little bracket around it, and I'm going to multiply each term, which I'm allowed to do, by a negative 2. So now, negative 2 times this term gives me a negative 4x, and that's what I was looking for. Now, negative 2 times the negative 3y gives me a positive 6y. And negative 2 times 7 is a negative 14. Now, the equation, you might say, is not the same anymore, but it's equivalent because I multiplied every term by the same value. Now I put my line, and I'm going to add them up. So this, through addition, is 0. This is going to be 11y, and this is going to be a negative 11. Okay. So now when I solve for my letter y here, I get, divide both sides by an 11, I get y equals a negative 1. So in my ordered pair, I get my y value as a negative 1. Now, what I do is I take this negative 1 and put it in either of our original equations. So let's use the bottom one here. So this will be 2x minus 3. Now, what is our y value? We're going to put it in parentheses. Is a negative 1 equals 7. So this is 2x. This is going to be a plus 3 equals 7. Now I'm going to subtract 3 from both sides, and I get 2x. I'm subtracting 3, transposing that. This is a 4. Divide both sides by 2. X equals 2. So my ordered pair solution then is 2 comma negative 1. Now I put these values into my original equations, and we see that both of them are true. This is the point of intersection, and we arrived at it by using the addition method, that is modifying one, or in some cases both, equations so that one of the letters will cancel out. All right, let's go to our whiteboard, or from our whiteboard back, and we'll see what they're going to do. And they're using a similar process. And they're getting the y as a -1, and then eventually solving that, or putting that in the other equation to solve for the x value. We get x is 2, and there it is. Nicely worked out by the authors, and I did it too. And here is the check. All right. Now, they are bringing us back to what I initially showed you in the beginning, the various possibilities of these two linear equations. They're going to be completely different lines where they will intersect at only one point. That's exactly one solution. Here is a case of parallel lines. Again, there would be no solutions for these. And then here, one line is actually on top of the other. So the lines, even though the equations may have been disguised and didn't look like they were the same equation, they were. And the proof is the lines are on top of each other. So here, there's an infinite number of solutions, because every solution for one equation is a solution for the other equations. Okay, so again, repetition and emphasizing what we mentioned earlier. Now, in example 5, they're showing us a system of equations with no solution. So in a sense, these would be parallel lines. There would be no intersection. So what does an answer look like to indicate they're parallel lines? Well, here's our system. And notice we have it in standard form. So what we're going to do is modify this equation here by multiplying it by a 2. They're not showing you this. And then it becomes this. So now when we add them up, these cancel out. These cancel out. We end up with a 0, and we're left with a 15. Now, does 0 equal 15? No, that's false. So when you do something like this, and your answer is an untrue statement, then that indicates there is no intersection, in a sense, no solution. And going back to sets is an empty set. And this circle with a line through it is the symbol for an empty set. And if you were to plot these, you would see they are, in fact, parallel lines. This is a continuation of example 5. Okay, let's look at example 6 now. Again, there are systems of equations, and notice they've solved for the letter x. So this is the value for x. If I take that and put this value for x in the other equation, which is what they're doing right here, and then distributing, getting rid of the parentheses, combining like terms, we notice that the y's cancel out. And all we're left with now is a -40 equals a -40. Is that a true statement? Yes. This indicates that these equations, even though they were disguised, are the same equation. And let's prove that, by the way, by taking this equation, 5x, and we're going to solve for x. So we transpose the negative 20y to the other side, or it becomes a positive 20y, and then a minus 40. And now we divide everything by 5, and we get x equals 4y minus 8. The same equation, it was just disguised. So when we do and solve it for either like we just did, solving for y, or using one of our methods, substitution here, or if you did it by addition, it would come out the same. Okay. So how would you describe the answer? Well, there's an infinite number of solutions. The equations are dependent, that is, they're the same equation. And a way to write this in set builder notation using braces, x comma y, that's the ordered pair, is such that you just mention one of the equations, and you could use either one. That is, the equations represent the same line. All right, let's go on. Now, for our last few examples, we're going to look at what is called the break-even point. Here, a company that manufactures running shoes has fixed costs of $300,000. Additionally, it costs $30 to produce each pair of shoes, materials, electricity, manpower, and the shoes are sold for $80 a pair. This gives rise to two functions, and take some notes on this. Now we have a cost function, which we're going to use C, and we say the cost C of x is equal to, I like putting this in the beginning here, 30x. That is $30 for each pair of shoes, cost of production, plus the fixed cost of $300,000. Now you might recall this is in the form of y equals mx plus b, where b was your y-intercept from an earlier lesson, and m is your slope. Now, what would be the revenue function? Well, we're using R for revenue, so R of x, remember x is the number of pairs of shoes, is equal to, you're going to sell each pair for $80. Now, you want to find what is called the break-even point. Now, remember, we can always substitute the function symbol with a y. So in a sense, this is y equals this, and this is y also. Y equals that. So we're now, in a sense, given the possible equation of y equals y. All right, let's set that up. And we'll go to the whiteboard. I have it up here. So this is one value of y. This is the other value of y. So what do we do to solve it? And I'll get rid of some of this stuff here. Well, we're going to subtract 30x from both sides, and this gives me 50x equals 300,000. Divide both sides by 50. I did this ahead of time, and this is 6,000. So if we sell 6,000 pairs of shoes, that'll be a point of intersection and what we call our break-even point. And let's see it now back in the slides. So there are two equations, y equals this, y equals this, and when we solve it, we get x equals 6,000. Now, another point is how much money would have been generated through the sale of this? That is, what is your y value? Well, if you put 6,000 in this equation, replacing the x, we get $480,000 were taken in to reach that break-even point. And above that, if they sell 6,001, they start to make a profit. The thing is, they have to get that fixed cost paid for. So how many pairs of shoes, the profit of those shoes, are needed to be sold to meet this amount of money? Okay, well, we've had some interesting ways of solving systems of linear equations. In our next topic, we're going to see where instead of just two equations, we're going to have three. Gets a little more challenging.